Today I'm here to talk about some aspects of slope stability analysis, especially for objects with a complex geological structure. My presentation consists of the following parts. First will be short introduction about my company, my university. Then second, words about slope stability analysis methods. Then we go to building geometry and boundary conditions. Next, we will say about parameters in short way. Then about meshing and size of parameters in relation to a factor of safety values, because this is a very important thing in slope stability analysis. And after this, few examples, and then at the end, summary. Okay, so at first, few words about AGH. AGH is one of the largest Polish technical universities, and at the Faculty of Mining and Geoengineering, numerical analysis have been performed for many years at the request of external companies, both from mining and construction industries. The main activities are focused on slope stability, tunneling, gas storage caverns, and foundation system. You can see here some example of model built in GTS by us. On the right, there is a tunnel which actually is constructed now in Poland. This model was built by one of our students at master degree work. The second picture below is one of our biggest model built in GTS MX. This is biggest salt mine in Poland. Okay, here are some information about me, and then I say some words about slope stability analysis methods. There are few methods from classical limit equilibrium methods through numerical methods like shear stress reduction method. About the stability problem. This is problem of many parts of our life. Here we have some landslide on near the road, then some problem with stability of railway embankment, also a problem with highway embankment. Then we have the next photo of problem with railway embankment, and here we have some problem with old open pit mine stability. Now this pit mine is filled by water, but during the filling, one of the biggest landslide in Poland occurred, about 400 meter wide here. The biggest landslide I've analyzed it in my life was one of open pit mine dump landslide of about 600 million tons. This was the biggest landslide in Poland I've known. Okay, about shear strength reduction method. It's the most popular method in slope stability analysis in numerical methods. So if we have stress state in some element of our model, and we have more Coulomb criterion. We have, for example, 25-degree friction angle and 10 kilopascal cohesion. So in this situation, we have on the screen model is stable, so because we don't have we don't have plasticity limit in this element. We don't reach this limit. Then we divide strength parameter by factor of safety. So we divide cohesion and tangents of friction angle. If we divide it by 1.25, everything still is okay. Model is stable. The same as we divide by 1.5. There is also no problem with stability. But if we divide by 2, the model is unstable, and program cannot find the solution. So we're bracketing these numbers, and for example, in this example, for factor of safety 1.67, we have found the solution of our problem. So we can say that that factor of safety of this element is 1.67. When we make stability analysis, we must choose between 2D analysis and 3D analysis. In past years, most of analysis was performed in 2D. But now also the computer power and also possibilities of software allows us to analyzing problem in 3D. So when to choose 3D? If geometry invariant in direction of perpendicular to transverse planes, for example here. In this example, we choose 2D analysis. For these parts, we should choose 3D analysis. Okay, so if no 3D model, if yes, we should check if geology is invariant in the direction perpendicular to the section plane. If also the simple water conditions exist. You can see here some complicated geology structure. So if yes, we should. If no, we should choose a 3D model. If yes, we should check if load is constant in direction perpendicular to section plane. If no, constant, then 3D model. If yes, we should choose 2D model. In most popular programs to stability analysis, which are limit equilibrium method, there is also a big problem with 3D models, because if we model some with limit equilibrium methods, there is problem to choose the correct slip surface. There are some programs of 3D analysis analyzing in limit equilibrium method, but I don't use it because there is always problem with this correct slip surface. And this problem doesn't occur with numerical methods that use the shear strength reduction. So now some words about geometry and boundary conditions. First, geometry for 2D models, then geometry for 3D models, and then proper boundary conditions. So if we want to build geometry for 2D model in GTS NX, the best way is to, for me, is to use CAD files. for example, consisted of closed polylines, then we can import this by the module import AXF, and then we have this closed polylines, which we can transform to planar surface. Then then we can also check. It is very easy in this program. We can check duplicate elements. So we can check if all geometry is good prepared. Then we can generate mesh. Have also few possibilities. For example, auto phase. And if we choose this auto phase and click on the advanced option here, we can choose between element type, which can be tree plus quad, or sometimes only triangle, or sometimes only quadrilateral. We can also check this higher order element, which is very important in numerical analysis of slope stability, because linear function of shape elements are not good for slope stability analysis. So we usually should check this option. And after this, we can easy mesh all the model, which is quite fast, because in this program, when we are meshing, all threads of processor are used. Another problem is with building a 3D model. There are some possibilities in software to build this model. For example, we can use a terrain geometry module, but in this example I used so-called grid phase. So I have prepared some grid phase in program to generate some grid phase, and then I can import it by load option and generate a 3D model. And the last part of this section, boundary conditions. In 2D analysis, usually people get the right boundary conditions. So we have on the bottom line in X and Y direction fixed, and on the side part of the model only in X direction. But when we look at boundary conditions in a 3D model, sometimes people fixed all bottom and side planes in all directions. This is not good way to calculate factor of safety in 3D analysis, because we can overestimate factor of safety. The proper boundary condition in this model is also fixed in all direction in bottom plane, and fixed in perpendicular direction at side planes. Okay, now some words about parameters. The issue of the soil parameters in the stability analysis is a huge topic suitable for a separate presentation. So I will focus only on the values of deformation parameters, which sometimes are not given in documentation. So let's look about Young modulus and factor of safety in stability analysis. This is a simple slope with Poisson ratios 0.3, 20 kilonewton per cubic meter unit weight, friction angle 50 degree, cohesion 15 degree, and cohesion 30 kilopascals. And we have made calculations of this model for 3 different Young modulus. For all of these calculations, slip surface looks exactly the same. And also the factor of safety, if we look for example, with 5 megapascal, we have factor of safety 1.45. For 50 megapascals, we have also 1.44. And here for 500 megapascals, we have also 1.44. So we can see that that influence of Young modulus on factor of safety is very, very small. So if we only calculate factor of safety and we don't need to know the formation of the model, so this is not important to know exactly what is Young modulus of the soil. Very important section of modeling stability is to properly choose of mesh size and mesh type. So now I say some words about the effect of the element size and element order on factor of safety. First, on the simple example, which we have slope on the subsoil, 10 meter slope, 45 degree angle of the slope. And I've made this calculation for 3 variants of soil parameters. First variant, P1, when we have in slope also big value of friction angle and quite good cohesion. Then in variant P2, we have very big friction angle, 45 degree, and almost no cohesion, 1 kilopascal. It is good to use even small value of cohesion. For example, if you have in documentation that cohesion is 0, it is better to put in calculation, for example, 0.2 kilopascal, and even reduce factor of safety, for example, reduce friction angle for about 1 degree, because it will improve stability solution. Okay, and the third parameter variant is when we have in slope a big cohesion and small friction angle. Okay, I've made these calculations for 2D elements, triangle and quadrilateral, and for 3D elements, tetrahedral and hexahedral. GTS can also make the mesh built in tetrahedral element and hexahedral element. These calculations were made also for linear shape of shape function of elements and quadratic shape function of elements. So we can see here 8 types of elements I've made this calculation for. And the number of elements, you can see from about 600 elements for the coarse mesh, the coarse mesh, to about 500,000 for the finest mesh. Okay, that is how this mesh looked for 2D model. In this coarse mesh, we have about 10 elements per height of slope, and 20 elements in this model, height 40 elements in this, and about 80 elements in this model. And these are meshes for triangle elements, also the same meshes, but for quadrilateral elements. This was for 2D model, and for 3D model we have also the finest mesh, which was made by extrude the 2D mesh in this direction. Okay, to analyze the results, I've calculated some value which I called linear dimension of elements. Here we can see the equation for linear dimension elements for triangles, for quadrilaterals, for tetras, and for hexahedras. And then after making the calculations, let's look at the results. So in the first variant, where we have quite big friction angle and also some part of cohesion in strength parameters of slope, we can see that for triangle elements with linear function of shape, when we have quite big elements, so about 10 elements per slope height, the value of factor of safety is 1.4. When we reduce the size of the elements, the factor of safety is going down to about 1.25 for about 80 elements per height of slope. So we can see that the factor of safety for these elements, 2D elements, triangle shape and linear shape of function, there is very big difference between factor of safety for coarse mesh and for fine mesh. Also for quadrilateral elements with linear function of shape, we have big difference between coarse mesh and fine mesh. It looks better for elements with quadrilateral function of shape. So we have here almost no difference between coarse mesh and fine mesh. It is about 1.08 for this mesh and about 1.12 for coarse mesh. The same graph for 3D elements, and we can also see that when we choose linear function of shape for elements, we have a very big difference between the value of factor of safety. So we should choose generally quadrilateral function of shape, so elements with higher order. The same for example P2 for 2D and 3D elements, and when we have mostly cohesion in soil, the same as previous. When we choose quadrilateral function of shape, everything is okay. When we choose linear function of shape, the results are very dependent on size of the mesh. The same analysis I performed for most for more complicated structures. This is one of dump of our open pit mine in Poland. And here we have some results: displacement, or in solid strain E equivalent. This is what we usually show when we want to show the slip surface of the landslide. And we can see that this 4-noded or 8-noded elements are not so good. We have a big relation between size of elements and factor of safety. But when we choose this 8-noded and 20-noded element, the difference is much smaller. So when you performing factor of safety calculations, it is normal in finite element method. You should choose a higher order element to be sure of the results. Also, if you performing back analysis to calibrate model, for example, of this size element, you should also in the next calculations choose the same size of elements. Okay, and now some examples. First will be about analysis of two-staged slope, because if we are analyzing complex geometry in finite element method, this is a problem with finding the slip surface with the lowest of the slip surface of overall slope, overall model. Okay, let's look at this example. We have two-staged slope. One slope is 45 degrees, then the second is 40 degrees. So if the material is uniform, of course, this factor of safety of this part will have the lowest value, and this part will be will have the higher value of factor of safety. And when analyzing is performing by limit equilibrium method, we can see that here with Bishop method we have a value of factor of safety of 0.92. For this part we have about 1, and for overall stability about 1.23. When we put this model in infinite element program, for example GTS-NX, and we solve the problem, we will have only value of factor of safety for this part of model, so the first stage. The value is quite similar to this from Bishop, but what to do if we want to calculate factor of safety for this part and for this part? So the one way is to put the higher parameter in some part of the model. So we can exclude this element from this one group and put it to another group, and give here, for example, cohesion 10 megapascals. And then we solve the problem, so we can have the factor of safety of this this second stage of the slope. And when we give a higher value of cohesion in this way, we can calculate factor of safety of overall model, which is also quite quite good as in Bishop. But you can see that that the shape is not like in Bishop. This is very important that the shape in numerical analysis is not circular or like in many program in limit equilibrium method, but is going to the lowest value of factor of safety. Okay, and now some examples of real problem. This the first is Bełchatów lignite open pit mine. We can see one photo from satellite and one photo from the ground. Bełchatów coal mine is largest mine in the center of Poland. The annual coal production is around 50 million tons. The length is about 12 kilometers. The width is about 3 kilometers, and the depth is more than 300 meters. It also has very complicated geological structures, which cause numerous stability problem. So we have made many calculations for this mine. This is one of example. So we put here the real geology from the numerous of boreholes, and then we can calculate factor of safety, which was not good because it was below 1. So in reality we have a landslide here. So it was a good agreement with the reality from this calculation. We can see that landslide is going through a weak layer of soil here, and the result in plane strain equivalent. The second example is Świerki open pit mine. This was a Melafir mine located in the southern part of Poland. The leveling of the area within the deposit is approximately 70 meters. And as a result of the exploitation carried out almost continuously from the first years of 20th century, the northern slopes of Słoneczna Kopa and Czarna hills were successively undercut, which over time led to activation of the local landslide process. What is typical for this was the place when the landslide have been. What is typical for this type of landslides? The first symptoms are tension crack. This tension crack were about 1 meter width and about 8 meter depth when we found them. There's another photo of this tension crack, and so several boreholes have been drilled, and at a depth between 20 and 30 meter, the presence of very weathered rock material was found. So we have made a 3D model of this example. This project we had 3D CAD file of mine and surrounding land surface. Nowadays we often use point clouds from laser scanning or aerial photogrammetry to build the surface of the model. Okay, and this is the mesh for this model. We can see 4 layers. This one first is ground. The second is weathered rock, highly weathered rock. The third is moderate weathered rock, and the fourth is Melafir. We can see that the mesh is densified in this part when the landslide could occur, and in part we have when we have a big parameter, strength parameter, the mesh was coarse. And what I would like to show you is this: when we choose linear function shape of elements, the factor of safety was about 1.56. That was, of course, not a good result because there were tension cracks, yes. But when we choose a quadratic function shape, the factor of safety from the parameters we have from laboratory was about 1.2. So once again, you should choose quadratic function shape to slope stability analyze. And also the map of solid strain equivalent. Okay, and at the end, some example of railway embankment. This was located on very poor soil, so there were some problem with stability, and the aim of the study was to evaluate the concept of securing the embankment with the CFA piles here, okay, and CG injection in this part. So we have injection in this part, which cost improve soil parameters, and some piles, CFA piles in this part. And we made some calculations to calculate factor of safety, and the factor of safety, this part after the improvements, were about 1.9. So this was good. And summary of my presentation. So the first, numerical methods are a good alternative to the limit equilibrium method in 2D calculations because we don't need to define the slip surface. The second, numerical methods are a useful tool for 3D slope stability analysis. But you should remember that there is influence of the element size and the way of discretization on the obtained results. It is better to use a higher order elements. In my opinion, GTS is a user-friendly tool enabling to the performance of slope stability analysis both in plane strain and also in 3D state of stress. Geometry builder and mesh generator are very effective and powerful compared to some other finite element method program. It also allows excellent control on a project, and some example at the end. GTS also provides very advanced possibilities of work staging analysis. Here we have some work of our students. I put this, play this film. Okay, so we have very staged, about 100 stages that there were made here, and the largest models realized by us in this program in GTS-NX consisted of approximately 2,500 solids, about 46,000 surfaces. After meshing, this model was approximately built by 70 million tetrahedral elements. Model dimensions 4,700 meter to 4,200 meter to 1,250 meters. And now we are preparing even bigger model, and this model works very good. the meshing is quite fast, or even very fast. There is only some problem sometimes with searching adjacent faces, which took a long time, but after this the meshing is very fast. Okay, that brings me to the end of my presentation, and thank you for your attention. Now, if you have some questions, I can reply on it. Okay, so the first question is, how do you import? Sorry, we have problem with this screen. How do you import the geological MIDAS GTS? What's the format used for that? Geological surface I usually import by grid surface, or if I have some information from boreholes, I can make some points and connect it with surface. How to calculate the safety factor? The second question. In GTS, we have many options of analysis, and one of them is SRM analysis, strength reduction method analysis. So we choose this type of analysis and we run it. Importing the XF file might be also used in dam or tunnel structure. Okay, that is a good question. For example, this big mine, I have built the model. Many parts of this model was built in CAD file. Then in CAD file, I can choose to convert it to 3D faces. If I convert this CAD file to 3D faces, it can be imported by GTS, and I can connect it to build a solid. Okay, if I have a solid, I can cut this solid. I can cut the solid from the rock mass, for example, if I want to build a tunnel. So it is very good connected with CAD files, I think. What about the system requirement? It depends on how big the model is. The biggest model I showed here needs about 128 gigabytes of memory to make a mesh for this model, and processor is 28 threads, if I could remember. Okay, so it's 9 o'clock, so thank you very much for your attention. If you have some questions, you can also write to me on kowalski@agh.edu.pl, and I try to answer on this question. Thank you very much.